Welcome everyone. Warsaw, this institute, famous semester, which is consecutive 2 weeks part of the program. Number fractals. The speaker is Károly will be first lecture of this mini course for the title list. One parameter feminist IFSs. One parameter feminist of hyperbolic system of Bárány.
Thank you very much.
It is yours.
And thank you for the opportunity for giving this course. It's my great pleasure ever to come back to Warsaw. Really, very much like to be here. So what I would like to talk about, well, the title is over there, but today, so all new results are joined with Bárány, Solomyak, and Śpiewak. I am not going to talk about the new results during the first talk. During the first talk, I would like to give a general introduction, so it may be rather well known, whatever I say, so certainly it is for a considerable part of the audience. I just like to mention that this general introduction heavily based on our 14th chapter of our book, which is about to be finished, joined with Bárány and Solomyak, and we will finish it very soon. So it's okay, so I am not going to give all details. So that book is about self-similar self-profound fractals, and these are neither of that, but this is the last chapter of that book where we just go a little bit beyond that. Okay, so first of all, I just like to mention, it's good to start with the definition of the Hausdorff dimension. I believe that everybody knows that, but still I like to recall it. So if we are on RD always, and if we are given a T, which is non-negative, we can define, and the subset of RD lambda, and we can define its Hausdorff T-dimensional Hausdorff measure in the following way, that we choose a delta, which is positive, and we define this set function, what you see in this bracket, in order to define it, for this delta, we consider the delta covers of the set lambda. Delta cover means that it is covered and the diameter is smaller than delta. These are the delta covers, and for the delta covers, we want to optimize this yellow sum, but you see over there, we take its infimum. And then as delta tends to infinity, it is delta tends to 0, it is the same as taking the supremum of delta, then we get the T-dimensional Hausdorff measure. Now, if T is small, then this T-dimensional Hausdorff measure is infinite. If T is bigger than a certain number, then it is going to be 0, and when it jumps down from infinite to 0, that value is the T-dimension, that value is the Hausdorff dimension of the set lambda. Now, the strange thing is that I usually like to use two projectors. Now, the second projector is very tiny, but I hope that it is visible even for far distance. And usually, this is the place where I refer to later on when I need to refer back to stuff that I earlier spoken about. Now, I just like to continue introducing some notation that we use. This is the lower and upper local dimension. So if you have a Borel probability measure on a metric space, then the lower local dimension of this measure at the point of this plate is given by this lim inf of the logarithm of the measure of the ball. Bxr stands for a ball centered at x radius r, and divided by the logarithm of r. I believe that most of you are familiar with this. but I still, for those who are not that familiar, I just like to say that the meaning of this local dimension, let me say this local dimension, I would just abbreviate it as the underline. So instead of this complicated thing, I would just like the underline, and then this means, very roughly speaking, well, this is in particular if the limit exists. So this is the lower local dimension, and the upper local dimension can be defined similarly. We just write lim sup instead of lim inf. And if the lim sup and the lim inf gives the same, then we say that the measure is exact dimensional. That the measure is exact dimensional if this lim sup and lim inf are the same, and for almost all x it is a certain constant, then we say that the measure is exact dimension, and this dimension is d. Then the meaning of the fact that the measure is exact dimensional can be somehow expressed this way. So if you pick a point x and the small ball around x, and you would like to understand what is the measure of this ball, then the measure of this small ball is approximately r to the power d. That is the local dimension. Now, sometimes we need to restrict ourselves to measures which are nice measures, and the collection of these nice measures is denoted by MA. So A is a subset of RD, and we collect the Borel measures whose support contained in A, and the support is compact, and the measure of A is positive and finite. These are somehow the nice measure defined on the set A. And sometimes we also talk about the Hausdorff dimension of a measure. There are two kinds of Hausdorff dimensions, actually, the lower Hausdorff dimension and the upper Hausdorff dimension. This is going to be the upper Hausdorff dimension, actually, because we take the infimum for those sets whose complement has measure 0. Sometimes people say that you take the infimum for those sets which sets has positive measure. If you allow more sets, so a wider collection of sets with positive measure, then the infimum can be smaller naturally, and that is the lower Hausdorff dimension, and this is the upper Hausdorff dimension of the measure. Okay. And then connection, oh my God, to the connection between the Hausdorff dimension, Hausdorff dimension of the measures was defined over there, like here. I have this way. So it was like here, and the connection is that the Hausdorff dimension of the measure is more than equal to the Hausdorff dimension of the set. So if mu is a nice measure, I define what is the nice measure with the collection of nice measures, that is MA. And if mu is such a nice measure, then the Hausdorff dimension of mu is a lower bound than the Hausdorff dimension of A, because usually when we compute the Hausdorff dimension of the set, to give the lower estimate is the more difficult one, and most commonly we give a lower bound on the Hausdorff dimension using something related to measures. And that's why it's important. So the Hausdorff, usually we just find a good measure from this family MA, and then we would like to estimate this the Hausdorff dimension of this measure. So how can we relate the Hausdorff dimension to the local dimension? The Hausdorff dimension of the measure is the essential supremum of the limit of this ratio, which ratio appeared here. when we spoke about the local dimension. But in many cases, when our measure is an ergodic measure, then instead of the essential supremum, you just have that for almost all x. So in reality, in most cases, instead of this, you have for almost all x, and instead of limits, you just have limit when the measure is nice. But this is a general formula which is for all measure, but for the nice measure, you have limit, and the limit will be the same constant for almost all x. Okay. So now we come to the iterated function systems. So iterated function systems during this series of talks, it is always a finite list of contracting mappings. In general, it could be on a complete metric space, but this complete metric space will be on RT always. And the number of the mappings in the iterated function system is always little m. So whenever I have little m, it is always the number of the mappings. And then the first thing, if you are given, so these are contracting, strict contractions, each of them. And whenever you have such a list of mappings, then you would like to define the attractor, and the attractor is what remains after infinitely many iterations, basically. So what we do it is that we choose a ball, because they are strict contractions. You can choose a ball, B, let me say a closed ball, which is sent into itself by all the mappings of this iterated function system. All of them send the ball into itself. And then we start to iterate. Whenever during this talk I write Si1in, I always mean such as iteration, what appears over there.
Károly,
Yes.
did you say SI are affine maps or just in general?
No, just strict construction. Strict construction. During this talk, it will be mostly not strict construction.
It means distance is strictly.
Let's say which is smaller than 1, such that it is contract. So the rigid constant is smaller than T. Uniformly for all mapping. So it's very important that it's contraction. Yes. So you just choose a ball, can be very big, but sufficiently big enough that all mappings sent into itself, and then these are the n cylinders relative to this ball. Now I'm going to use it again. So yes. So what happens it is that you take all the n cylinders, and the union of all the n cylinders contains the union of all the n plus 1 cylinders, just because this happens on the first place, that when you apply 1, it is always a subset of B, and that's why the union of n plus 1 cylinders contained in the union of n cylinders, and then the attractor is given by this formula. So you just take the union of all level n cylinders, and then you take the intersection. So this is what you have after n iterations, the total what remains after n iterations, and then this is what remains after infinitely many iterations. Yes.
It probably means something. Do you assume that the maps SI are globally defined on the whole space, or contractions, or only locally on some subset containing the ball B?
Yeah. It's enough that it is defined locally on a subset which contained. It doesn't need to just contained. Yes. It's enough. Yeah. So this is the definition of the attractor, and the attractor satisfies this kind of like self-similarity like equation, that it is the union of its image, and this follows immediately from the definition. From this definition, it follows the lambda is the unique non-empty compact set which satisfies this equation 5. And so this characterizes the attractor. Now, the symbolic space, as I mentioned, M always stands for the number of mappings, and then the symbolic space is the one-side infinite sequences above this alphabet 1 to M. Perhaps the best, I'm sorry, this is a little bit small, so maybe now I need to change. Hopefully you see. Do you see this? Hey, can you read these letters, please tell me? Is it possible? So if you can, because the next one, this is really tiny, but this pi, which is the natural projection during this sequence of talks, pi always stands for the natural projection. So you just take an element of sigma. Sigma is going to be always it's 1 to m raised to the power n. So the element of sigma is something like this I1, I2, and so on. This is an infinite sequence. And then what is pi I? So the official definition is over there. So for example, if you want to, if your I is something like what is that? 2, 1, 2, 2, 1, 2, and so on. Then you form pi I. So this is I for you. This is an infinite sequence. It starts here. Then this is S2, and then because the first digit was 2 and the second digit is 1, so you are in this interval, and the third digit is 2, so then you are in this interval. And then you see that it is a nested sequence of intervals, closed intervals, and it will collapse into one point, and that point is pi I. This is the natural projection, the natural coding. Thank you very much. The natural coding, which is officially defined in this way. This is the official definition. Perhaps with a picture, it's better to see. So this is the natural projection. We code the elements of the attractor. The coding is not unique, and most of the problems I am going to talk about during these 3 occasions come from the fact that the coding is not unique in general. If the coding is unique, then we know pretty much like everything, or almost everything. Maybe you can ask questions what you don't know, but when the coding is unique, then we don't have problems. But it is very, very interesting that just in the simplest situation, when all the mappings are singularities on the line, there are very important questions. Nobody knows the answer in case of overlapping. So it's a very interesting thing that the structure of these overlapping systems is very complicated. So because the problems generally come from the overlaps, how heavy the overlaps, we need to introduce a couple of definitions related to how heavy. If there is no overlap at all, then we say that the strong separation property holds. This means strong separation property, as you know, that lambda is the union of Si lambda. And then when these sets are disjoint, oh my God, these sets are disjoint, the cylinders are disjoint, these sets are disjoint, then we say that the strong separation property holds. In picture, the strong separation property means that if you think of this picture, this is a typical example of strong separation property. Everybody has exactly one code. This is the nice trivial case. Now, the other one is the open set condition. There are some light overlaps. For example, all of you have seen, let me say, the Sierpinski-Karpi. The Sierpinski-Karpi is a similar set where there are 8 contractions and the first contraction sends this big square. This is 2/3, this is 1/3, this is 1/3, this is 2/3, and sends this big square here, the second here, the third, and so on. But this is left out always. This is going to be the Sierpinski carpet. So the open set condition, for the open set condition, the Sierpinski carpet, so this is S1, 0, 1 square, and this is S8, or the 0, 1 square. So this is a typical example for the open set condition, because if you take the interior, of the square, it serves as an open set. I'm sorry, I just here is the open set condition written. So the open set condition holds if you have an open set, like in this case, the interior of the unit square, such that this open set is sent into itself. This is the interior of this striped squares, sent into itself. And then when you apply the mappings of this open set, then there is no intersection. You see that here, actually, there is intersection, uncountably many points, but when you just apply for this open set, then there is going to be no intersection. So this is a typical example of open set condition, a typical example of the situation when we do have overlaps, but the overlaps is not significant. Thank you very much. So this is these are some separation property. Now, I am going to talk about mostly iterated function systems like the one on the right-hand side. These are going to be called hyperbolic C1 plus theta iterated function systems. It means that not only assume that the derivative exists, but the derivative is nice enough. And on the left-hand side, what you see it is a self-similar iterated function system on the line. You see that in both cases we have overlapping. This one doesn't want to work, just a moment. Okay, so you see that there is overlapping because the image of this interval is this blue, and by the red, this red, and this red and blue intervals, they intersect each other. So there is overlap in the system. Similarly here, there is overlap in the system. So the object of our consideration are the C1 plus eta iterated function system. The official definition is here. So I is a compact non-degenerate interval, and this is an iterated function system, which is called C1 plus eta hyperbolic on I. If Fi, like on the picture, sent into itself, the derivative is strictly smaller than 1. It is not 0. We do not allow the 0 derivative. And there exists an open set such that Fi extend to a C1 plus eta diffeomorphism, so an open set which contains I such that Fi sends this V into itself as it is indicated on the picture. So these are the objects what we are going to do here. We would like to understand them, study them. But the problem is that when you are given one iterated function system like this with overlaps, then in some cases you can say something. For example, anti-Károly such a profile have written very, very interesting papers when the so-called weak separation property holds. The weak separation property is similar to the open set condition. If very, very roughly speaking, it allows that somehow the open set conditions, what happens in the simplest case? Let me say you have a self-similar system, and you consider, let me say, self-similar system and homogeneous. So all the level and cylinders share the same length, let me say. Now, how can you visualize the open set condition in this case? The open set condition, so one more time, I'm talking about system which is self-similar and homogeneous. This means that SIX is A times X plus TI. This is something like what I'm talking about, and I is from 1 to n. Now, when do you have open set condition in this situation? You go to the level n. And let me say this is one level N cylinder. So you have open set condition, if and only if there exists a positive epsilon with the following property. You take any n you wish, and this is a one N cylinder, and this is a second N cylinder. And then, because the system is homogeneous, their length is exactly the same as I showed you. Now you take the distance between the endpoints like this, and you compare this distance. Do you see the distance I'm talking about? You take the distance and you compare it to the length of the cylinder. And the distance divided by the length needs to be bigger than epsilon. If the distance, this is arbitrary n, any n you like, and any n cylinder you like, and this is another n cylinder, and you take the distance in between the endpoints, you compare the length of this distance compared to the length of the cylinder. And if this ratio is bigger than epsilon, you have an epsilon that independently, whichever n you take, the ratio is bigger than epsilon, then you have open set condition. This is the way you can visualize open set condition. Now, what is peak separation property? Almost the same. But it's allowed that if you take two N cylinders like this and that, it is allowed that the two N cylinders totally overlap. The total overlapping is allowed, but if they do not totally overlap, then the same must apply. So there is an epsilon such that the difference, this is an arbitrary N, an arbitrary level N cylinder, and another arbitrary level N cylinder which does not totally coincide, so the distance is positive. So if the distance is positive, then the distance divided by the length of the cylinder is bigger than epsilon. This is the weak separation property in the simplest case. In the more complicated case, there are more epsilons, but this is the way to think of. Now, such a prototype, and again, what we have beautiful result about the weak separation property, but it happens. It happens rarely that weak separation property holds. And other than that, if you cannot prove that you have weak separation property, but you have intersection, heavy overlap like this, then you can do very little with one single iterated function system like this. You can prove little about that. So we need to consider, instead of one individual iterated function system, a family of iterated function systems with overlaps, and we can say something for a typical member of this family, not one individual member of the family. Yes. But in order to work, oh my God, oh yeah, it's okay. So in order to do this kind of things, we need some notation. So this is an iterated function system on a compact interval, and the hyperbolic can see 1 plus eta, and we have usually we write A for this alphabet, and then we define a metric. Now, actually, the distance, there are actually two distances. We use mostly this distance. This is the distance on the symbolic space, but we mostly like, except at one case, this is going to be the distance. So this is the distance on the symbolic space. And this is a good distance on the symbolic space, because if you use this distance, then you can define the Hausdorff dimension on the symbolic space itself. And the Hausdorff dimension for this distance on the symbolic space is going to be the dimension what we expect to have on the attractor. That's why this is a good distance. So what you do it is that you take I, which is an infinite sequence from sigma, and J, which is also an infinite sequence from sigma. And then you consider I by J. I will use this notation I wedge J very, very frequently. So this is I1, IN, this is a finite word. If it is true that I1 is equal to J1, IN is equal to Jn, but IN plus 1 is already not equal to Jn plus 1. If this happens, then I wedge J is equal to I1, IN. So this is the common prefix. I wedge J is the common prefix, and you apply the mapping Fi wedge J. So what does it mean? One more time, Fi wedge J. In our case, this is Fi1 IN, and recall that we use this definition Fi1 FIN composition, and then we apply this on the and we take the length. If we are on the line, but usually we are going to be on the line during this talk. Thank you very much. Yes, and then we use this common notation. We write this sigma for the left shift, and then a Borel probability measure invariant if this holds. So sigma minus 1h has the same measure as h, and it is ergodic. I always assume when I say ergodic that it is invariant. And if you have sigma minus 1h equal to h, then this can happen only if the set h is a set of full measure or a set of zero. So one of the two ones is zero, and one of the two ones is zero, and the other one is one, sorry. So this is the ergodic measure. And what is the entropy? I just like to speak about entropy in a very, I believe most of you know what is entropy, but I'm not sure that everybody knows what is entropy. So I just like to say a word about that. We have a measure. This is the collection of ergodic measures. So we say what the measure is ergodic, and then you just take a measure which is an ergodic measure. And what is the entropy? So what you do it is that you take an infinite sequence, a typical infinite sequence. So you take a mu typical element of the symbolic space. And then you just restrict yourself to the first n digits. So this is I, so I is like I1, I2, and so on, the infinite sequence. And then you consider I1, IN, and we use this notation I1, IN cylinder, which means all the elements of J from the symbolic space such that J1 is equal to I1 and Jn is equal to IN. So this is the cylinder. This is the cylinder which appears over there. Now, what is the entropy? If you take a mu-typical element, then as you choose a fixed mu-typical I, and as you increase n, you go with n to infinity, then this set is getting smaller and smaller, because there are exponentially many sets like this. Its measure tends to zero exponentially fast, and the speed with which the measure of a typical n cylinder tends to zero, the speed with which it tends to zero is the entropy. So this is the entropy, very roughly speaking for us. And there is another thing, the Lyapunov exponent. This is also very important, the Lyapunov exponent. I'm pretty sure that Mark Polikot is going to give a talk on Wednesday, perhaps, about how to compute the Lyapunov exponent, because it's not easy to compute it. It is very difficult to compute it actually precisely. So what is the Lyapunov exponent? Compared to the entropy, yet again, you take this x is just an interval such that all fi sends this interval into itself. And then you fix yet again a mu-typical element of the symbolic space. And for this mu-typical element, you consider the n cylinder And because there are exponentially many n cylinders like this, its length tends to 0. And then the exponential speed, the speed with which it tends to 0, is denoted by T mu, and this is the Yokohama exponent. It can be written in this way. So this is the definition of the precise definition. If you want to transform this something really meaningful, then you get this orange definition. This is the Yokohama exponent.
How smooth it is. How smooth.
Very smooth. I mean, 1 plus epsilon.
So it could take any point.
If it is ergodic. So it's if you just take a typical point and then the length of typical when it is ergodic, then it's good. Now, what is the Hausdorff dimension? When we speak about the Hausdorff dimension of nu, I actually said something about that. If you remember, at the very beginning, I spoke about this kind of things like local dimension. Do you remember all this? Hausdorff dimension of mu. In a very beautiful case, this essential supremum is just for all x, so almost all x, and the limit is just lim. And assume that we are in a beautiful case. So it's ergodic beautiful case. So the Hausdorff dimension of mu is supposed to be something like this. What you see over there. Instead of the ball, what we do, here it should be a ball. But what we do, it is that we just take an n cylinder, the measure of an n cylinder, because if you take a point, any point from the attractor, that point is contained in an n cylinder. So this is from the attractor, then you will find at least one n cylinder, maybe more than one, something like this, which contains this point. So this is an I1, I, and X. And then it can happen that this is X, and you take, this is an X which is contained in this cylinder. This is not exactly the ball what you have here. Not exactly the ball, because this ball is centered at X, you know, but it is almost, something like that. And then if instead of really the ball, you just take the measure of this n cylinder and you divide by the logarithm of the length of the n cylinder. This is almost like the radius of the ball. If you take this, then this nu was the push forward measure. You know what is the push forward measure? So usually what we do it is that usually we have this sigma, which is the symbolic space e to the power n. And then we have the natural projection, and here we have the attractor lambda. And basically always, when we want to have a meaningful measure here, it is a push-forward measure. That is, we consider a measure mu on the symbolic space, and we push it forward, and that is going to be nu. So nu h is the nu measure pi minus 1h, and we just write that this is the pi star mu. So this is the push forward measure. So for this push forward measure, if everything is beautiful, if you don't have any overlaps, we are in the strong separation property case, then this n cylinder is not intersected by any n cylinder. So this n cylinder on the attractor is the image of the n cylinder in the symbolic space, and that's why this measure is the same as that measure. As I mentioned when I spoke about the entropy, very roughly speaking, the measure of such an n cylinder for a typical I, the measure is something like this. and the length of for a typical eye is something like this, very roughly speaking. And then if you make the algebraic manipulation, then you get that this is entropy divided by Okunov exponent. So if you have an ergodic measure and this iterated function system has absolutely no overlaps and everything goes well, then what you expect is that the dimension is equal to entropy over Okunov exponent. You could see that actually I made a slight inconsistency, because in the definition it is written that we need to consider the logarithm of the measure of a ball divided by the logarithm of the radius. Now you can do this kind of trick. Instead of taking such a ratio, you take the logarithm of a measure of an L cylinder divided by the logarithm of the length of X cylinder, and the Kaimaki and your student Reeves or you had a joint paper, and that was, I think, proposition 3.8. that you can, if you have open set condition, maybe weak separation property, so it's a well separated, then in this situation you can make such a trick. So instead of they proved it, so we don't need to do it again, that instead of such a ratio, you can consider the ratio which is over there, which is much more handy to take. This is for a typical F. So for a new typical F, instead of the new typical F considering this ratio, you can.
So you want to say that in place of considering all balls, you can consider only cylinder.
Exactly, and that's much more convenient, because otherwise.
Yeah. Another remark, I was of course stupid saying that you can remove integral, because then you need to one else and then.
Yeah. You can remove, but that's a different one. Yes. So you can do this. It's good to know that maybe and can remind the name of the course. It starts with R. Yeah, Rossi. No, but Rossi. Yeah. Okay, good. So similarity dimension. So now what I'm going to do is that we have 2 minutes before the break, and then after the break. Although my goal is to speak about C1 plus eta hyperbolic systems, but I cannot avoid talking just a little bit about the self-similar systems, because there are similarities. In particular, for the self-similar system, the solution of this yellow formula is called similarity dimension, and that is the best guess for the Hausdorff dimension. Now, in the C1 plus eta case, we get the very best guess in a similar way. But first, we need to go through this, and I suggest that we should have a 10-minute break. Is it okay? 10 minutes. 10 minutes. According to this is not good otherwise, because this says that it's 15. So it's self-similar. We have this self-similar iterated function system. As always, we have mapping split constructions of the interval I into itself. Ri are the contraction ratio. They cannot be zero, but anything between -1 and +1. And then here is this magic number, which is called the similarity dimension. I will write it on the whiteboard, because we will come back to this number several times. So SI X is like RIX plus BI. This is the important thing, the RI. And the similarity dimension is just the solution of the equation RI raised to the power S is equal to 1. So the similarity dimension does not depend on DI, does not depend on the translation, or how you translate these mappings. it depends only on the slopes. So this is the similarity dimension, which is the best candidate for the Hausdorff dimension. So if you have open set condition, then Hausdorff dimension of the attractor is equal to S. So, so this is a self-similar system, and even the S dimensional Hausdorff measure is positive and finite. If the positive and finite, if you have open set condition. So, but otherwise, it's not necessarily true. And so this is the solution. And then, what is the natural measure? As I mentioned, when we want to give a lower bound, we usually will need some measure. If you want to get the dimension of the attractor, then you would like to consider the natural measure, because you see that these elements sum up to 1. Therefore, these people, what you see over here, can be chosen as probabilities, because these are positive and they sum up to 1, so they can be considered as probabilities. And from these probabilities, you just form a probability vector. This is the m components vector of probabilities. And then the natural measure is defined on the symbolic space as the infinite product measure of this probability vector. And the natural measure on the attractor is the push forward measure of this mu p. So we have already spoken about this definition, what is the cylinder on the symbolic space. And then for this measure, the measure of a cylinder is just the product of the corresponding probability. So this is the push forward. And then you take the push forward, and then you get the natural measure on the attractor. Okay. And then it is an interesting thing that if you take the natural measure on the attractor, and then what happens is that if you take a Borel subset of the attractor, then the S dimensional, this is S, the S dimensional Hausdorff measure of the set is constant times the natural measure, which is very interesting. Constant times the natural measure. And then here is an interesting field. I cannot stop not to talk about that. What is actually the exact dimensional Hausdorff measure for a nice set? All of you know, for example, the Sierpinski. This was the carpet, but I know the Sierpinski gasket. You know what is Sierpinski gasket? I don't need to draw it. You know what is Sierpinski gasket? And this Sierpinski, but still I draw it. The Sierpinski gasket. This is all the lengths are equal to 1, and then the iterated function system sends this triangle. All the sides are equal to 1 into this is, let me say, S1 T like triangle, S2 T and S3 T, and then you repeat this. This is the Sierpinski gasket. And then everybody knows what is the Hausdorff dimension of the Sierpinski gasket. You just, because we have open set condition, just the interior of this triangle is the open set. So what you have, all the contraction ratio is 1/2. So 1/2 and plus 1/2 to the power s is equal to 1. So you get s is equal to log x3 divided by log 2. This is the Hausdorff dimension. And then people can ask a very simple question. What is the exact dimension or Hausdorff measure of this object? And people don't know. I had a very, very smart student. He was a classmate of Bárány. I had many very but that particular very smart student was a classmate of Károly. His name was Károly. He is working now work on, so he wants to earn money. But he is the person who knows the best approximation for this. And the best approximation, he was a person who in high school won not the mathematical competition in Hungary, but the informatics competition. And he managed to combine informatics with geometric measure theory to get the best lower bound for this measure. And it is something like the lower bound is 0.74 and the upper bound is 0.8 something. So still there is a considerable gap. People don't know. The very first thing what one would think is that maybe it is equal to 1. But if you think a little bit further, you will see that it is certainly not 1. And then it's very, very difficult. So because when we speak about how to compute this, if you just go back to the very beginning of this talk, the very beginning, it was the definition of the Hausdorff measure. The definition of the Hausdorff measure. How do you define the definition of a Hausdorff measure of a set, like the set over there? You would like to take the most economic cover, the most economic in these sets. Now, what I told you it is that this Hausdorff dimension is equal to S. What does that mean? It means that there is no more economic cover in terms of dimension than the most natural cover, the cover by n cylinders. There is no any cover, system of covers, which gives you better exponent. But this is not the best cover. What is the best cover? Nobody knows what is the best cover, but not the cover by cylinders. Because if this infimum was taken by the cover by cylinders, then it should be equal to 1, but it is not 1, it's less than 0.8, about 0.8, not 1. So we again.
Did your student try maybe also to calculate packing measure? I'm asking because for the maps of the interval, there is explicit formula for the packing, very simple formula for the packing measure for similarities. Due to a thing Fink and maybe in this case, I'm not sure whether this formula holds also for in the complex plane, but maybe, and this would be actually maybe easier to, it seems a little bit paradoxical, but it could be easier to calculate packing measures on Hausdorff one.
Yeah, it is absolutely possible, but Hausdorff, this is the best, and in his trick, the computer found the value. He didn't tell the computer what to do. So the computer needed to go on an enormous large tree. The computer needed to decide which are the branches of tree which are hopeless. So that he doesn't know what is the best cover. The computer knows what is the best cover. So it was not trivial somehow. So this kind of question, what is the exact dimension of Hausdorff measure for very, very similar sets, very simple sets on the plane, these questions are not easy because we just don't know what is the best cover. I'm sorry, this is not really the topic, but I couldn't. But there is something very important which is called complete overlap conjecture. This complete overlap conjecture is still open, and I believe that Andy is going to talk about this a lot a little later. I'd just like to mention a couple of things. So what is the complete overlap conjecture? Let S be the similarity dimension and the lambda is the attractor, and the Hausdorff dimension drops. So the Hausdorff dimension is not equal to the minimum of the dimension of the space, and the similarity dimension, this little s is the similarity dimension, if and only if there are two mappings which completely coincide. So there are two mappings such that one of them is absolutely useless. I cannot stop just giving you the most characteristic example what you may think of. This is like if you consider a set lambda, which is, let me say lambda, which is sum of ak times lambda k, and k is from 0 to infinity, and ak can be anything from 0, 1, and 3, but not 2. So not AK cannot be 2. And this is going to be for a fixed lambda, this is a Cantor set. Now when lambda is equal to 1/3, then what you have it is that if you write always 0, then you start with 0. If you write always 3, then I think you end up with 9/2. And then if you write for the first 0, then it will be 1/3 of this, so it will be 3/2. And you start also, so this is the interval where you will end up if you start with 0. So I call it interval I0. And when you start with I1, so for 0, k is equal to 0, you write 1, then you start here, and the length is the same, 1/2, so it comes to here. And finally, if you write for the first k is equal to 0 term is 3, then you start here. So this is I3, and this is I1. And here you have overlapping region. Now, if you go to the second cylinder, the second level, then you see something similar. And this is a second cylinder over here. And here you also go to the second level. You get this kind of people. And the interesting thing is that this is I started with 0 because, and then this was the rightmost. So this is I3. And this is I1 0. And these two intervals totally overlap. It means that S03 is the same as S10. This is a beautiful example. You can keep it in mind because whenever you hear the expression D separation property and or measure D separation property, this is a canonical example of an iterated function system with D separation property. And when I hear listen to mathematics, they tell me some complicated notion. I'm happy to think of something simple which satisfies that. So this can be an example which comes to your mind. So this iterated function system is like SIX is 1. In general, it is 1 x plus I when I is 0, 1, or 3. But this particular case was lambda was equal to 1/3. So the similarity dimension would be equal to 1 because you have 3 contractions of contracting ratio 1/3. So the similarity dimension is 1, but the Hausdorff dimension, because of the fact that these two people totally coincide, the Hausdorff dimension is 0.8 something, so it's even smaller than 0.9. Okay, so this situation of complete overlaps happens, for example, here. So this is the complete overlap conjecture that the Hausdorff dimension is always equal to the solution of this equation, except in the case where you have complete overlaps, so when you have a phenomenon like this. So when you are not in this phenomenon for a self-similar set, that the dimension doesn't drop means that it cannot ever be bigger than the dimension of the space, but so the minimum of the dimension of the space and the symmetry. Now this is a complete overlap conjecture. Now what can we say about this complete overlap conjecture? First of all, that this is not true in higher dimension. The following example, I heard the example from Yuval Perez, and I don't know whom to contribute the example, but the picture is over there, and here is that. So what we do it is that I would like to show you an example on the plane where the complete overlap conjecture does not work. So there is going to be no complete overlap over here. And in spite of that, the dimension is smaller than the similarity dimension. And the similarity dimension is smaller than 2 because we are in the plane. So what we do it is that we yet again consider this set. This set is related to the 0, 1, 3 problem. So this set is considered again. this set is considered. But now lambda is from the interval 1/3 and 1/3 plus epsilon. You choose a small epsilon and you choose 1/3 and 1/3 plus epsilon. And then this is the set what you have here on the x-axis. So this is the set. You see this, and that. This is the set. Which set you have. This is the algebraic description of the set. But as I drew this picture for lambda is equal to 1/3. Now we take lambda a little bit more than 1/3. Now, if lambda is a little bit more than 1/3, then it has been proven, I think it was Solomyak who proved it first, that if lambda is bigger than 1/3, we haven't investigated this set with Mark Polycott, but only in the regime when lambda was smaller than 1/3. So when lambda was bigger than 1/3, it was, I think, Solomyak who proved that for a typical value of lambda from here, the Hausdorff dimension of the attractor is equal to 1. So here you see that the dimension, because what we consider it is a fractal of the plane, and this fractal will be the product of two fractals. One of the two fractals, the one which is on the x-axis, is written in this way, and then it starts like this. And the other one is a very simple fractal. You see, this is lambda, and this is lambda, just two intervals. And the length is 1/3 plus epsilon. So it's 2/3. You see that they are far away from each other. There is no any overlap. Okay, and then you take, so basically consider a very simple fractal satisfying Stokes separation property here on the y-axis, and this much more complicated fractal, the one that you see over there, you consider this complicated fractal on the x-axis, and you take the product of the two fractals. Is it clear what we are doing? So, what do you have then? Then you have an iterated function system. Basically, the product will be the attractor of an iterated function system which consists of altogether 6 mappings. This big square is sent onto this one, onto this one, onto this one, you see, and so altogether 6. So then you have 6 mappings, and the contraction ratio for each of them is equal to lambda, and lambda is slightly bigger than 1/3. So what you have, this is written over there. So what you have it is that the similarity dimension of the system is equal to this, because you have 6 mappings, each of them have contraction ratio lambda. And then if lambda is small, just a little bit more than 1/3, then this is smaller than 2. Okay. Now, what is going to be the Hausdorff dimension? So this is the similarity dimension. And then what is going to be the Hausdorff dimension? So this is the similarity dimension. Log 6 divided by negative log lambda is the similarity dimension of this two-dimensional self-similar iterated function system. Now, what is the Hausdorff dimension of this? This is the product of two fractals. And both of them are very regular. Therefore, the dimension of the product will be the sum of the dimensions. But, as I said, for a typical value of lambda, this set has Hausdorff dimension equal to 1. The other set, the one which is on the y-axis, you see, it is very simple because this is lambda, there are 2 of them. So the Hausdorff dimension is going to be this ratio for the fractal on the y-axis. So the sum of the two, as you see, is going to be the dimension, the real Hausdorff dimension of this self-similar set. But this expression, easy to check, is smaller than that. And this is smaller than 2, so the minimum doesn't appear. Okay, so on the plane, the complete overlap conjecture doesn't have a chance. And this is a very simple example. A very simple example. It's annoying that it was not me who found it. But when I was told by Yuval Perez, I was angry that this is easy. And because this came right after that Boris Solomyak proved that for Lebesgue almost all lambda, this is really equal to 1. So somehow the point is that here on the x-axis, the similarity dimension on the x-axis is bigger than 1. But on the x-axis, nobody can have dimension bigger than 1. Okay, so then you lose dimension. You lose dimension on the x-axis. But you do not lose dimension on the whole system. That's the idea. So this is an easy and I think beautiful common example. So it doesn't work. You cannot do it on the plane. But the same cheap trick, of course, cannot be played when we are on the line. The same cheap trick cannot be. So the complete overlap conjecture is still open, and Andy is going to talk more about that. But Hofmann had a little bit more than 10 years ago, actually it was published 9 years ago, but it was announced at a conference in Hong Kong, 2012, December. So it's marvelous, that's a marvelous theorem of Hofmann. And this is what I would like to talk about. So this system is now on the line, and this is a self-similar system. And we need to define this expression delta n. What is this delta n? The smallest distance between the left endpoints of two level-n cylinders having the same length. So how do you define delta n? You go yet again, choose an n, any n like this, any n like you want. And you take two cylinders. Let me say this is one of them, and this is the other. If these two people have different lengths, then their distance is going to be infinite. So because this is not necessarily a homogeneous system, it can happen that two level-n cylinders do not have the same length. And then the distance of these two cylinders is infinite. But if two level-n cylinders have the same length, then your distance is just the distance of the appropriate endpoints, what I'm indicating with my finger. So this is what you see over here. So this is the distance between the level and cylinders. This is the way to write down the distance between the level and cylinders. And then Hofmann says that the exponential separation condition holds if you can find the positive epsilon and the sequence of integers which tends to infinity, such that this delta nk, sorry, it was the minimum distance. So I told you what is the distance of two cylinders. If they have different lengths, then their distance is infinite. If they share the same lengths, then their distance is what you see here. This is the distance. And this is the distance of, and then you take the minimum possible distances for a given n, and this will be delta n. So first you define the distance of the cylinders, and then on a certain n, you take the minimum distance in between two cylinders. This is going to be delta n. And when you have delta n, then the exponential separation condition holds if there exists an epsilon and the sequence tending to infinity, such that this delta nk is big, is sufficiently big, is bigger than epsilon raised to the power nk. This is the exponential separation condition introduced by Hofmann. And what Hofmann says it is that if the exponential separation condition holds, then whichever p you choose and you consider the self-similar measure. What is the self-similar measure? The self-similar measure which corresponds to, so if here is this your iterated functional system, and then you take a probability vector p, and then you consider the infinite product measure which corresponds to this probability vector, and you push it forward. then you push it forward. So this is the infinite product. And then you push it forward. And the push forward of this infinite product measure is the self-similar measure, which corresponds to this, probability. So this is a self-similar measure, and for every probability vector, the corresponding self-similar measure has the Hausdorff dimension of 1 and the similarity dimension of nu, and the similarity dimension of nu is just the entropy of nu divided by the Lyapunov exponent of nu, as I indicated earlier. So this is minimum, and the similarity dimension entropy divided by Lyapunov exponent. This is, it means that the dimension, I told you earlier that if the cylinders are well separated and the measure is ergodic, then this ratio should give you the Hausdorff dimension of the measure. And then what Hoffman says it is that if the exponential separation condition holds, then for every self-similar measure, the dimension of the self-similar measure is what it has to be. And this is very important because from this, it easily follows that the attractor, the dimension of the attractor is not going to drop. And this condition, this exponential separation condition, holds very frequently. The exceptional parameters for which it does not hold have packing dimension 0. Packing dimension 0, not only Lebesgue measure 0, not only Hausdorff dimension 0, but packing dimension 0 is stronger than Hausdorff dimension 0. If you don't know what is packing dimension, then you just take Hausdorff dimension 0. Okay, this is even stronger. So not only that, for almost all parameters, it holds an exponential. Not only that for almost all, but the back one, the back parameters, not only set of 0 measure, but even set of 0 Hausdorff dimension, even set of 0. So this is an active data due to Hoffman. Yeah, and then there is a good piece of news. I'm sorry for saying that. We do not have anything similar for the C1 plus eta situation. So it is doesn't solve completely the self-similar situation, but it solves. One more thing what I would like to say it is that what else do we know? Even Hoffman already 9 years ago could prove that if all the parameters, what I show you, all the parameters are algebraic, then we have the complete overlap conjecture. So either there are two cylinders which totally coincide, or if there are no such two cylinders, then the dimension doesn't hold. And then Rappaport, I see 2020 proved that if only you assume that Ri are algebraic, you don't need to assume this, but only assume Ri algebraic, it's enough. If only the contraction ratios are algebraic, you have the complete overlap conjecture. So either two cylinders totally coincide, or if not, then the dimension has no problem. So there are beautiful results in that time, but this whole theory is very much for self-similar. Hoffman and Boris Solomyak extended it to fractional linear mathematics, but because it is kind of finite dimensional, so it's but in general we don't have this, and what we have is the transversality. This is what we would like to, what I am going to talk about, the transversality method, what we have for this C1 plus epsilon. So first of all, now we come back to our mappings, which are this conformal hyperbolic 1 plus C1 plus eta mappings. So we leave the self-similar situation. When I suppose finish.
So you still have 20 minutes? Okay.
25. I started 25. Oh, no, sorry. Because I think so 15. 15. 15. Okay. Good. So we go back to this, and then we would like to know. So what are we talking about? We are talking about yet again this kind of systems. This system, what you see over here. And you have such a system, and you would like to know what should be how to define the host of dimension. It is defined the host of dimension, but what is the best guess for the host of dimension? For example, in the case of self-similar systems, the solution of this equation does not always give the host of dimension, but it gives you the best guess for the value of host of dimension. Now, we would like to get an intelligent guess for the value of host of dimension in the case of systems like this. So what we do is that we just take this I, interval I, what you see here, this is interval I, this is I1, I2, I3, these are the first cylinders. And then you go to the nth cylinders. You form this set. These are the nth cylinders. And then you would like to do something like this equation, So you write down this. This is the length of an nth cylinder. You raise it to Sn, and then you solve this equation. If we have a look at the previous situation, like this, if you raise this equation to the power m, then what you get it is that you raise the left-hand side to the power m, so RIS, and you raise it to power m, to power n, thank you. Then what you get it is some I1, IN, R, and R, I1, IN, IN, raised to the power s is equal to 1. And this is by definition Ri1 multiplied by Rin. So if you just raise both sides to the power n, then this is what you get. And this is the length of an n cylinder approximately. So for every n, the same S gives you the solution in the self-similar case. But if you are not in the self-similar case, if you are in a case like that, then for every n, you get a different solution. So this is not the same solution, but different in our case. However, the limit exists. And the limit is not very fast. So I mean, the convergence is not fast. And this is what Mark Polycott is going to talk about, I believe. And because if I am correct, Mark, maybe you can correct me, that the speed of the convergence is constant divided by n. So the speed of the convergence is constant divided by n. This is not update. Imagine that you have any a constant is equal to 1, and n is equal to, let me say, 10. You want to have 1 over 10 precision. Then it means that you need to go to the 10th level. If you have 3 mappings, then 3 to the power 10 summand you have here. Then you have 3 to the power 10 summand to solve the equation. And then you get 1 over 10 precision. So this is not really good. And Mark Polycott invented with Oliver Jenkinson, I think in the 90s, some very, very intelligent methods using very high-level mathematics. And it has been developed, and also Polymer Bitnova has results nowadays similar to that. How to actually compute this limit. Because this limit is going to give you the best guess, but this limit is not easy to approximate, approximate in a really computable manner. So another way to characterize this best guess, just a moment, sorry, I need to get that. So that to use this pressure function. So you can see that this pressure function pretty much resembles to this equation. If you would take logarithms, for example, you come up with this expression and you take logarithm on both sides and divide by 1 over n, so something like that. So it is not a problem. You see here, it was the contraction ratio. This was the contraction ratio. And here we just write the supremum norm for the derivative. There are going to be some bounded distortion theorems which say that if you do not take the maximum of the derivative, but you evaluate the derivative at any point you like, it is enough. But for the first, just have a look at this expression. And what we will prove later, I just wrote it down here, but we will prove it later, that this function is strictly decreasing and continuous. And at 0, if you write t is equal to 0, you will get log m. And if t tends to infinity, the expression tends to negative infinity. So it has a unique 0. And this unique 0 is SF. And it happens to be the same. So we will prove this, or at least I hope that we will be able to prove that this limit what you have here, and it is denoted by S sub F, and this is F in the bracket F. These two people are the same, and this is the best guess for the dimension. So basically, this SF corresponds to what we have in the similar cases, the solution of this equation. And the pressure is a very important tool because the pressure is somehow related to this equation, basically. And that's why it's important for us. Now, in our investigation, we will always fix, because as I mentioned, we assume when we consider this system, this is our system, we always assume that for every mapping, the derivative is strictly smaller than 1 and bigger than 0. So we just consider families of iterated function, hyperbolic iterated function system, families which consist of m mappings. This is the hyperbolic iterated function system on the interval I, which consists of m mappings, is denoted, the family of such system is denoted in this way. We always consider only mappings like iterated function system like this. And then you fix as you wish in any particular way you like. You fix gamma 1, gamma 2, which separates the derivatives from 0 and 1, and we will work with this system, because you can choose gamma 1, gamma 2 as close to 1 as you wish. All hyperbolic 1 plus theta smooth system are considered in this. Now, this is the Lipschitz constant. This is the Lipschitz constant for the system. So we take the supremum for I and X and Y, not exactly the Lipschitz constant, because here is theta, and our system is C1 plus theta. So just by definition, this almost Lipschitz constant, Hölder constant, or I don't know how to call it, this LF is finite. And okay, and then the norm, the 1 plus eta norm of a function is the maximum norm for the function itself. Sorry, the maximum norm for the derivative, and this constant LF, which is over there, this constant which is over there. So you add up these three people, and this is going to be the 1 plus eta norm of a function. Now, the distance in between two iterated function system is just you take the maximum for the elements of this system, because F and G are from the same branch, I mean from the same family. We always compare systems to each other if they are in this same class. So they are in the same class. System F and system G are in the same class, and then the distance is defined in this natural way. And this is a complete metric space. It is not difficult to see that in this metric, this is the metric, and this theta, gamma 1, gamma 2 is a complete metric space.
I have a question. Do you order the maps in some specific way? Say,
Yeah. We do that. Yes. Yeah. Now here are two things. I do not know how much you know about all of this, because when I prepare for such a lecture, I do not know the audience, and I don't know how much familiar you are with this story. May I think that everybody knows the first theorem at least, which is the bounded distortion property. And this bounded distortion property is a very, very important property, perhaps one of the most important property for the conformal systems, may I say. So this is an extremely important property, the bounded distortion property, but I know that not everybody knows about this, even working on dynamical systems. So what is this property? This property says that we fix as always gamma 1, gamma 2 to separate our system from 0 and 1. And then it says that there is a constant C, which is of course dependent on gamma 1, gamma t, such that if f is an iterated function system from, it's over there, so f is such an iterated function system, then it's a very, very important property. We always use it, basically always during the next talk. You take any n you like, any n. N is a finite number, and I is a word of length n. So I is something like I. So you take any n, and you take every word of length n, and then you take every x and y, whichever x and y you like from the interval, of course from the interval, and you compare the derivative of this function one more time. What was fi? Fi is fi1 composition fin. So this composition, well, it's derivative, of course, because, well, fi is this mapping. So you take this composition mapping and this derivative, evaluated the same mapping at x and y, and you take the ratio. Then this ratio is in between two constants, and this constant does not depend on n, does not depend on I, does not depend on x and y. This is a very, very important property, and this is called bounded distortion property. And any conformal system has this property. And there is the second one, because as I mentioned you, that we are going to consider families. And if you consider families, you can think of F and G. You see here F and G. This F and G, the way as we apply this second part of the lemma will be that F and G are from the same family for two different parameters. And we would like to compare almost the same, but a little different, because you see we compared here the derivative of the same mapping at different places. It doesn't matter. We learn from this. It doesn't matter if I write here x and y, because this 0 can be changed to x, and this 0 can be changed to y, just on the price paying with this constant. So it doesn't matter. What matters that here is a function fi, and here is a function gi. And fi is from this iterated, and this is from the other iterated function system. And the beautiful thing is that for their ratio, we can give some very nice bound. What is this bound? This is exponential, and the length of I, as you see, and just the distance between the raised to the power theta. This theta, if you don't want to be very precise, you can think that we are talking about systems not C1 plus theta, but C2, and then theta is equal to 1, and theta is equal to 1, so then C2 system. So if they are C2 systems, then in the exponent, this is just the distance in between the two function systems, and here this is the length. So the length appears, but it is less precise than the first one was, but still, this is good. Now, I do not really have time. This is the proof of the first one. You can see that the proof is completely elementary. It's absolutely elementary. Everybody can do that. If you go home on train or tram, sorry, you can write it down for yourself. And the second one, I'm sorry, I didn't prove it, is in our book. And I believe that, sorry, I have recovered last week, but still not completely. But okay, so in the 40th chapter of our book, this is also proved, and I believe I shall stop here.
Questions?
Yes.
So how much of this can be generalized for infinite IFS? Have infinitely many.
Marius knows infinitely many times what I was thinking. So probably we can answer that.
Okay.
Yeah, you still have see for this kind of balance formula or no overlapping, and this is a little bit more complicated because the zero may not exist, but taking over negative, so you have full control over dimension of the measures, and also then you can consider the families of IFSs. Actually, did it a little bit with Roy, and I mean, for overlaps, this becomes more interesting, and this is actually our joint work with you and Károly, sorry, and Boris.
Yeah.
Right. Yeah. So then you can also say something. So I think quite a bit of this would go for the case of Cantor. It's more complicated. Right?
More questions? So explain.